We want to talk about functions and function notation, something that you're going to deal with in a pre-calculus course, um, or in a second, Algebra 2 course, functions and function notation. Okay. Now, a lot of people do well in this course and subsequently take the pre-calculus, skipping the MDE 61 support course for pre-calculus. And often that works out, but in the majority of cases, it's not a good idea. People tend not to be able to make the jump from this course to the pre-calculus. But for those who can, and for anybody who's going to encounter functions and function notation at any point in the future, I'm going to do a little introduction here. Now, I've written a few things on the board. Function has exactly one output for each input. Okay, now what do we mean? It means I give you a number and you've got some idea in your head about what to do with that number. Okay, so I give you a number and you do whatever's in your head and you output another number. Okay, so I'm giving you inputs, you're giving me outputs. You can only give me one output. You can't say, if I give you the number 17, you can't say, well, 85 or 739. That's not a good answer. I want a single answer. I need a single answer if this is going to be a function. Okay? So that's what we mean by one output for each input. Okay? I give you a number, you give me a number back. Or if I have the idea for a function, you give me a number and I'll give you one number back. I'm not going to give you two. I'm not going to give you a dozen. I'm going to give you one number back. Now, it might be that I give you the same number for more than one input. That's okay. It doesn't violate the only condition is, that doesn't violate the only condition, which is that there's exactly one output for each input. It doesn't say how many different inputs might result in a certain output. Okay, let's see how that works out. Now I'm going to jump directly to the idea of a graph as a function. I assume everybody is familiar with a set of Cartesian axes, y versus x. Your x values are going to be your inputs. Your y values are going to be your outputs. Now to demonstrate how this works in a graph, I'm just going to sketch a curve here. Okay, there's a curve, just what my hand felt like doing at the time. This curve can define a function. If you have a scale for the x's and a scale for the y's. Well, I can define a scale. I can take any x value, any value on the x-axis and draw a vertical line. And for every point on that vertical line, the x-coordinate is the same as it is on the axis. So we're just saying, let's say this is the line x equals, you make up any number you want. But I'm going to say x equals 16 here. And I like to use powers of 2 to define scales for reasons that you'll probably see here shortly. And let's say that I want to do a scale on the y-axis. And I'm going to declare that y equals 0.8 here. Now, there's no requirement that these scales be identical. Although a lot of times when you're drawing introductory functions, you do want to use equal scales. And by equal scales, I mean, if this is 8, then 8's about here. You're going to use the same scale on the x-axis, and this sure isn't 16. This distance is not twice this distance. Okay, so if you try to use equal scales, you wouldn't have 16 here and 8 here. Okay, but you could have 16 here and 86,000 up here. There are plenty of functions that use numbers in maybe double digits that give you 5-digit outputs. Okay, well, anyhow, X equals 16 is your input. What's your output? Well, your output is what you get on this graph. It's the Y value you get on this graph at the point where the X equals 16 line, at the point where the X equals 16 line intersects the curve. That would be this point, and the Y value is whatever it is here, okay? So I'll say on this dotted line here, Y is the output for the input 16. Input is your X value, output is the corresponding Y value. The one rule is you get exactly one output for each input. So you can't have a curve. Let's say that I wanted to extend this curve and wanted it to double back over here. If it doubles back, then there's going to be another point where the curve crosses X equals 16. And you're not going to get just one answer. So again, coming back to the exactly one output for each input, you can't have the curve crossing the same vertical line twice, or in any case, more than once, okay? You can't have multiple crossings of any vertical line. That's the vertical line test, and it's very simple. You just get it in your head. Comes back to the basic definition. Okay, now I'm going to ask you to, and of course I understand that you're probably watching this as a video, especially since there's nobody in class today, end of the semester. And everybody's trying to do their homework using AI, so they're not learning anything, so they've given up maybe. There are other things. I mean, life can get in the way too. All right. So what I'm going to ask you to do is tell me if there are any other inputs that would give you the same output as X equals 16. And if so, estimate them. Okay, so again, estimate the inputs to result in the same output as 16. If there are, and if you think there are none, okay. If you think there are some, but you don't know how to estimate them, at least see if you can do as much as you can. See if you can locate points on the graph that would correspond to those inputs. Okay, you've had time to think about it. Hopefully you've engaged yourself, and hopefully you haven't just, I mean, this is not a question you can take to artificial intelligence, okay? You'd have to draw the picture for it and then enter the picture or draw it on a online sketch pad or whatever. It's not an easy question to ask of AI. It's a question you really have to think about, which is why I'm starting with this question. Okay. I repeat often, AI is a great way to learn things if you use it right. It's also a great way not to learn anything if you use it wrong. Okay. So don't let it do your thinking for you. All right. In any case, what do you have to think? You have to think in order to answer this question. We want to find inputs that result in the same output as 16. Well, everything along this line here has the same output as the output you get for x equals 16. Okay. The output for x equals 16 is whatever the y value is on this line. Are there other inputs that would give you the same output? Well, yeah. Right here is a point that has the same output. Okay. At this point on the graph, the output is identical to the input for 16, assuming that I've drawn this figure correctly. This line should be horizontal. This line should be horizontal, and they're not really completely parallel. So, there's some uncertainty in my sketch, but best estimate you can make for this sketch is that whatever x value corresponds to this point is going to be another input that would give you output, the same output as the input 16. So what I can do is I can draw a line here. And x equals what? Well, you got a scale. If this is 16, what's this? Certainly less than 16. It's less than half of 16. It's probably less than a fourth of 16. Maybe it's around 2 or 3. But it's negative on the negative side of the axis. Now, the curve actually does kind of, it kind of gets interrupted here, but it continues on here. And it actually, if you look closely, does seem to go through the curve. At this point as well. So it looks like there are 3 inputs that give you the same output. Now we can make estimates, okay? I'll explain why I like to use powers of 2 to define scales. I can cut 16 in half. I just come over the halfway. And I'm going to label this line x equals 8. And then I'm going to go halfway between 0 and 8. You get x equals 4. And halfway between 0 and 4, I get x equals 2. And it looks like this is just about as far to the right of the y-axis as this is to the left. So I'm going to make an estimate based on just subdividing 16. And if you start with a power of 2, you can always subdivide it using simple numbers and simple fractions. Okay, so I'm going to say that's x equals 2. That's probably x equals, I'm not going to try to do a fraction here. I'll just use a decimal. It's a little less than 2. It's certainly more than 1 unit from the y-axis. So I'm going to say it's about 1.8 units from the y-axis, and x equals negative 1.8. Now over here, x equals 16. What's the x value corresponding to this point? Well, it's about this far to the right of 16, and this far looks like it's just about 8. So if I add 8 to 16, I get x equals 24. Now I'm going to answer my question. It says, looks like equals negative 1.8 and x equals 24 yield the same output as x equals 16. And I should have said, looks like inputs. I want to reinforce the fact that your x values are the inputs and the y values are your outputs. Now we've done all that and we don't even know what the y value is. Okay? We didn't need to know what the y value is in order to identify all the points that have the same input as x equals 16. Now we could estimate. Graph's getting a little busy, so I'm going to use a different color here. Okay, here's y equals 8. If I come halfway down to the x-axis, of course, y equals 0 on the x-axis, half of 8 is 4. Let me say this line here looks like y equals 4. Well, if y equals 4 here and y equals 8 here, it looks a whole lot like y is pretty close to 5 on this horizontal line. I'll say by the scale, y equals 5. I can say now, we estimate that this output is y equals 5. The output y equals 5 results from inputs x equals negative 1.8, x equals 16, and x equals 24. That's the best set of conclusions I can right now draw from this graph. Now, this function has multiple inputs for some, has multiple inputs for some outputs. I'll just write down if you have multiple inputs for the same outputs, multiple x values that give you the same y value, function is not what we call one-to-one. What do we mean by one-to-one? That means exactly one y value for every x value. I'll just sketch a one-to-one function in a little bit of room I have here. Did you get the idea? This curve represents a one-to-one function because every input, no matter what input you use, no matter what vertical line you draw, no matter what x value you happen to choose, there's exactly one output for every one of these. None of these output lines cross the graph in two places. They kind of got to be using a video and a clear screen to see what I just did here. And we'll do more of this, but this is something, if you grasp it right now, it's going to save you trouble later, okay? And you can draw other graphs. Basically, if the graph is going upward and it's going to be one-to-one, it's got to keep going upward, okay? And if it's gone downward and it's one-to-one, it's got to keep going downward. And the one-to-one property is a very important one. Most functions are not one-to-one. Now, what do we mean with most functions? There's an infinite number of possible functions. Um, well, I'm not even going to defend my statement that most functions um, are not one-to-one. Depends on how you count them. You get the idea. Most of the functions you will encounter in a pre-calculus class are not one-to-one. Of course, you can encounter linear functions, which really should be a part of Algebra 2. And if you've had Algebra 2, you would know this. Any linear function is either going to be going up or it's going to be going down. Linear means it has a straight line graph. The only exception would be the linear function that's always got the same value. All the points are in the same horizontal line. Well, it's worth understanding that. So you regard that as a sign, is a kind of a side comment. The focus here is this definition. A function has exactly one output for each input. We draw a graph and ponder a bit what outputs and inputs mean in terms of this graph. Once you grasp that, it's much easier to understand graphs and much easier to understand functions. Now, sometimes we want to give a function a name. So I'm going to name the function of this graph. I'm going to call it f for function. So call the function for our graph f. So we can talk about it. Okay. Not a very imaginative name for function. And of course, we often use G or H for functions. We can use any letter or any symbol to represent the function. We could make up a symbol and say that this symbol is the name of this function. But we're going to use F, the least imaginative thing that we could possibly use. Given input 16, F yields the output 5. Given output 5, F yields this output for what numbers? Stop and think about it. Answer the question. Ponder everything I've said up to this point, at least everything that's relevant to this question. What does F yield? For what value? Yeah, okay. For what inputs does F yield output 5? Just another way of phrasing the same question in case you have trouble understanding this. So take time, think it through as best you can. It can be confusing when you first see it. It takes a lot of sorting out. which is why we're posing these questions so you can begin to sort all this out. Okay, hopefully you have an opinion. Hopefully you got it right. Given the output 5, F yields the same output for X equals, or for inputs. Well, for input 5, it gives you output. I'm sorry, for input 16, it gives you output 5. And we also saw that for inputs negative 1.8, 24, and of course, 16. Again, there are 3 inputs that yield output 5. Oh, it's output 4, not 5. No, it's 5. Okay, never mind. I saw that big 4 up there and all of a sudden confused myself. I do that a lot. Watch me. Okay, be careful. Don't believe everything I say until we're sure that I've said it right. But yes, okay, this is correct. For what inputs does F yield output 5? The answer is negative 1.8, 24, 16. All right, now, a little bit of a vague statement, but I think it's clear what it means. The inputs are X values, the outputs are Y values. Okay? We say that Y is a function of X. And that's a big deal. Not only that, we've named the function. We call it F. We abbreviate the statement Y is a function of X named F by saying we say that Y equals F of X means F takes inputs X, gives you outputs Y. Abbreviated, we'll say Y equals F parentheses X. So that X is something you put into this function. It's an input that results in an output Y. And we read this, Y equals F of X. We write it Y equals F parentheses X. Okay, well, let's say that instead of a graph, we've got a formula. Now I'm going to pull a little trick on you. Let's say that G is another function takes X values as inputs. And for a given X value, outputs X squared plus 1. Could have used any formula. There's a formula that allows you to calculate the output. So now, what are the outputs for inputs X equals 2, X equals 5, X equals negative 4. So for X equals 2, what is the output? For X equals 5, what is the output? For X equals negative 4, what's the output? Now I'm going to give you a minute to figure that out. Okay, now if you have good understanding of the question, you probably figured it out pretty quickly. If you don't have good understanding of the question, I'm going to say a few things that will hopefully give you a better understanding. Okay? So, I'm going to make the statement input X yields output X squared plus 1. It's a simple, more concise statement of what I just said up here. So make sure you understand that this whole paragraph comes down to this, and we can apply this to these inputs. So input X equals 2 yields output Y equals X squared plus 1 equals 2 squared plus 1, which is 5. Now that ran on a little further, and I wanted to, I don't know what word I'm kind of like an artificial intelligence, but not a smart, okay? I don't know what word's going to follow until I see the word I'm on. Because currently, in 5 years, our large language models will appear very primitive. But right now, the large language models simply take an immense amount of data, incorporate it, and then figure out what word to say next in answer to some prompt. Not really very smart, but it certainly seems smart as heck. So you got to watch it. And it'd be interesting to see what happens in 5 years. Hope I'm around to see it. Okay, so the input X equals 2 yields output Y equals X squared plus 1. That's what the output's going to be. And if X equals 2, that gives you 2 squared plus 1 equals 5. Okay? Then for X equals 5, you get 26, and for X equals negative 4, you get 17. We'll evaluate those in a minute, but I want to get to the notation first. Okay, now we can say that Y equals G of X, which is X squared plus 1. Get a little cramped for space here, sorry about that, okay? And unfortunately, G came out really faint, but I think you can read it. Let's ruin it by trying to make it better. Okay, that may be a little better. If x equals 2, then y, well, if x equals 2, we got y equals g of x equals x squared plus 1. If you replace x by 2, we get y equals g of 2 equals 2 squared plus 1 equals 5. We don't have to write it in this form to answer the question, but if we put it in this form, it makes things a little clearer and it makes it a lot easier to talk about this function because we've given it a name. It's the function g. Okay, well, since I have this definition for the function, which is exactly the same as what I said up here, but I put it more concisely. Okay, look at that. They gave you a description of this function g. Okay, ask you to figure out a few outputs. Then I said input x yields output x squared plus 1, which is a shorter way of saying everything I said here. And now we say the same thing by saying that y equals g of x equals x squared plus 1. That's pretty much all we need to know in order to answer the questions that I posed. Now, there are other things we want to know about the function g, like, what kind of numbers are going to come out of g? Well, we can answer that. You square any number, it's going to not be negative, so we add 1, and we're not going to get any numbers less than 1. But, okay, you don't have to remember that. Just another thing we got to know about functions. Another is, are there any numbers that we can't put into this function? Are there any x values that this function won't work on? Okay, no, function works fine on any number. You can square any number. Not always the case for different functions. Okay, now let's go back to the main event. Get this statement that describes a function. We get this whole development that describes functions. We've got this statement that shortens all of this. And then this one, it's kind of the ultimate shortened statement. And now that we have this, we can say, okay, now we want to find this for x equals 5. Well, if x equals 5, then y equals g of 5, which is 5 squared plus 1. And you can calculate that in your head. If you can't, you can use your calculator. But if you're using your calculator to calculate 5 squared plus 1, you're dumbing yourself down. No offense. We dumb ourselves down all the time. But you're unnecessarily dumbing yourself down. If you don't know what 5 squared is, you really need to learn to at least multiply any single digit number by any other without having to use technology. Use your head, because otherwise you won't have a head to use with artificial intelligence, or you won't have a head to use in finding your way around. If you happen to misplace your GPS, how are you going to get from here to there? Okay. And many other things in life. You just be less able to think and less able to function well. Okay. You make yourself, putting it positively, you make yourself more able to function well if you know these basic things, even though you could use technology to replace them. The technology doesn't enhance the circuits in your brain. Okay. Well, if x equals -4, then y equals g of 4, which is -4, which is -4 squared plus 1. If you're going to square -4, and of course the function says you've got to square x. If you write -4 squared without the parentheses and put that into many calculators, the ones that do it right, instead of, again, trying to dumb everybody down, It's going to square the 4, but it's going to apply the negative afterwards. It's an order of operations. In other words, -4 with the 2 up here means do the 4 to the second power and then apply the negative number. You put -4 in parentheses and you won't run into that problem. In any case, -4 squared is 16. -4 times -4 is a positive number because you got 2 negatives, and 4 times 4 is 16. Okay? So this is the way function notation looks. Now I'm going to make a table from function. Okay? Let's let f of x equal 2 raised to the x power. This is a different f, not the same one we'd graphed, not the same one we were talking about previously. Let's let f of x equal 2 to the x. I want to make a table. X in this column, Y in this column. And I'm going to use X values five, 4, 3, 2, 1, 0, -1, -2, and maybe we'll go further. Okay. Okay, if X equals 5, I'll do my calculation out here. My statement here reads y equals f of 5 equals 2 to the 5th because x is now 5, x is 5, and x is 5. We get this. Okay? And 2 to the 5th means 2 times 2 times 2 times 2 times 2. Right? Raise 2 to the 5th, you multiply 2's, 5 of them. Well, 2 times 2 is 4, 2 times that is 8, 2 times that is 16, and 2 times that is 32. Okay? If x equals 4, well, see if you can calculate as far as you can. You might have a little trouble when you get down to 0, or -1, or -2, maybe even 1. But go ahead and calculate what you can here and see if you can anticipate what I'm going to do next. And write it out, just the way I'm writing it out, because if you write it out with your hand, rather than typing it into or keying it in one way or another to some program, you don't retain it in the same way. You'll retain it better, and if you take the time to simply write these things out. Write every line the way I've written this line. Okay, I've given you time. First of all, I'm not sure this is the best word, but I'll write interpretation kind of from the head here. Interpretation of this for the given value of x. You're going to get y equals f to 4, which is 2 to the 4th. Yeah, let's review. That means 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So we're going to get 16th. And now we're going to get writing it out without as much comment. We don't want this video to get too long. 2 to the 3rd. That's 2 times 2 times 2. Times 2 is 4. Times 2 is 8. We get 8. then y equals f of 2, which is 2 raised to the second power, which is 2 times 2, which is 4. Y equals f of 1 would be 2 to the first power. Well, that just means 2, just one up. Now we get y equals f of 0 equals 2 to the 0. What's 2 to the 0? A majority of people coming into a pre-calculus class will tell you that 2 to the 0 is 0, meaning that there are some things that are taught in algebra courses that simply don't take. I can't imagine that not taking, but that's because the way it was taught back 100 years ago when we chiseled our work into the walls of our caves. Okay. Okay. Y equals f of 0 equals 2 to the 0. What is that? Let's look at the pattern of these numbers. How is 16 related to 32? Well, 16 is half of 32. Okay. You should know your numbers and divisions and so forth well enough that that's obvious. Should be even more obvious that 8 is half of 16, 4 is half of 8, 2 is half of 4. So what we're going to get here, if we follow this pattern, if the pattern is valid, is half of 2, which is 1. Okay. Well, that's not overly difficult. Okay. Now that is a rule. Okay. Any number to the 0 power has to be 1. Now that's generalizing what we see from this pattern, but there are reasons for that rule that we'll talk about later in case you missed it in your prerequisite courses. Okay. Now that means if we go down, if x goes down another 1 from 0 to -1, we're going to have to take half of that. If x goes to -2, we're going to take half of a half, which is a fourth. You know, if you've got a pie, say this is a pie, okay? And let's say it hasn't been eaten out like this one has, okay? There's half of it, right? Cut it in half. Now cut each of those halves in half, and you got 4 pieces. So you got 1/4 of a pie. I say that because not everybody has really mastered that much of the idea of fractions. And that's a fault of the curriculum. You learn fractions in 5th grade and then never use them again. Okay, so x equals -2. Your value of f of x, f of -2 will be 1/4. We can now take this rule, this arithmetic rule, and we can make a graph. Okay, now actually, I want my x-axis to be somewhat lower. And since I smudged this up so badly, see smudges on the board, but we'll live with that one. Okay, I'm going to do this again, except my x values go all the way out to 5. On the other, okay, if this is my y-axis, my x values go all the way out to 5. My y values only to -2. Also, all my y values are positive. None of them are negative. So I put the y-axis way down here and give myself room to go out to 5. Okay? Now I can mark a scale 1, 2, 3, 4, 5. Here's 5 on the x-axis. I'd like to draw the line x equals 5 instead of labeling 5 there, because if I label 5 there and my graph is below the axis, it could go through my label and mess everything up. But there's x equals 5, and here's x equals 1. And we can draw the lines for x equals 2 and x equals 3, and x equals 4, and I'm kind of missing them, but you get the idea. And then we go over to -1 and -2. I like to draw the vertical lines. I don't like making a huge grid, labeling everything from -10 to 10 and so forth, unless it's appropriate to the function. Okay. So anyhow, now we want numbers that go all the way up to 32 on the y-axis. Now on the scale here, from -2 to 5 is only 7 units. I'd have to go almost 5 times that far in the vertical direction if I was going to use the same scale. So I'm not going to use the same scale. I'm just going to declare that y equals 32 here. So let's see. When x equals 5, y equals 32. So we're going to put a point here where the line, vertical line x equals 5 meets the horizontal line y equals 32. Okay, that was easy. Now when x equals 4, y is 16. Okay, so x is 4 here. I'm not going to label it, but there it is. Okay, and y's got to be 16, which is half of 32. How do we get half of 32? Well, from 32, here's 32, here's 0. We go halfway, and we say that this line halfway from here to the x-axis must be the line y equals 16. It intersects the line x equals 4 at this point, and there's another point on our graph. Now, when I wrote y equals 16, I wasn't watching. I didn't write a very good 16, so let's write that a little better. Okay, then y equals 8 when x equals 3. Well, here's the x equals 3 line. I'll go ahead and label that one. And we're going to go to 4, which is half of 8. So it's going to be half as high as this one. So we go half as high here. There we got it. Okay. And then when x equals 2, I think I said that all right. Okay. This is half of this. This is 16. Half of 16 is 8. Now, it actually looks like I am a little high for the halfway point. We try to get as close as we can to halfway. Okay. Then half of 4 is 2. So let's see. That would put the x equals 2 line meeting the y equals 4 line, and the y equals 4 line would be here. And then the x equals 1 line should meet the y equals 2 line. The y equals 2 line will be twice as close to the x-axis as the y equals 4 line. So it's getting a little hard to label these. I'm not writing very well either. Okay, y equals 2 on this line, and then y equals, yeah, that's where x equals 1. And y equals 1 when x equals 0. Well, the y equals 1 line is halfway, and the y equals 2 to the 1. So here's y equals 1. That's going to give us a point here. And then where are we going to put 1/2 for x equals -1? We got to go halfway between the x-axis. Well, it's got to be twice as close as this point to the x-axis. So it's going to be maybe here. And twice that close is going to be practically on the x-axis. So there is the pattern of our numbers. And we can draw a nice blue curve through these points. It's clear that if we keep going to that through the negative numbers, from -1 to -2, then -3, -4, -5, and so forth, that we're going to keep going halfway to the x-axis. And the blue line is going to pretty much just look like it just merges with the x-axis because these lines have thickness. A geometric line, an ideal line, has no thickness, and this curve will never touch this line. We say it's asymptotic. It's an asymptote. We say it's asymptotic with x-axis, meaning he's going to get so close it just blends with it, even though in reality it doesn't. This leads to my preferred construction algorithm for the 2 to the x function, which is incidentally our toolkit exponential function. It's called an exponential function because the variable x, the input x, is an exponent. So it's an exponential function. Since the input x is an exponent. Now, here's my basic construction for the shape of any exponential function. I've got a rectangle here. This one looks kind of like a square, but it's okay. Cut it in half. Now, each half I cut in half with vertical lines. There, I'm done with vertical lines. Okay? Now, I cut it from the top, I go halfway to the bottom, just like I was going halfway up here. Okay, so I go halfway to the bottom. And then I go halfway from there to the bottom. And halfway from there to the bottom. And halfway from there to the bottom. Then I make a mark on the left edge on the lowest line that I constructed. I call these dotted lines construction lines. Okay, so I go to the left edge, lowest construction line. Move over one, up one, over one, up one, over one, up one, over one, up one. And I get a shape that's identical in form to this shape. Scale's a little different, and I've got more points on this graph. So it actually gets steeper than this one ever gets. This picture is adequate for a hand sketch model of just about any exponential function that's increasing as x is increasing. Want a decreasing exponential function, we flip this thing around and go decrease. Want an exponential function that exponentially approaches some line up here, we just flip it this way. Okay, now that's very brief, but that's kind of a picture of the way I personally ask people to be able to construct an exponential shape. Okay, now my intent wasn't to analyze exponential functions. I'm just using this, but it's one of the easiest graphs to make. So I'm using this to illustrate how the function notation is used. Okay. Let's just do one more thing here because we're having so much fun. Let's say I want to draw the line y equals 12. And now I want to say solve f of x equals 12. Well, that means we want to find f of x is your y value, y equals f of x. So to say f of x is 12, it's mean to find the x, the input x, that gives us output 12. Well, I see that this y equals 12 line intersects the graph here, and I can draw a vertical line here. It's between x equals 3 and x equals 4. So I can label the x equals 4 line here if I want to. And it looks like it's, it's these lines are a little wiggly and stuff like that. But I'm going to say this may be x equals 3.2 and make a little kind of wavy equal sign here. So x is approximately equal to 3.2. Now you put it into your calculator, raise 2 to the 3.2 power, and see how close I got using this graph. I don't think I got all that close, but it'll make things plausible. And if I want to estimate find f of (2.5). Well, where's 2.5? Here's x equals 2. So x equals 2.5 would be halfway between 2 and 3. That's your input. To get the output, you just go up to the point where we intersect the graph with the x equals 2.5 line and estimate y equals whatever. Well, if this is 4 and this is 8, that looks to me like about 6.7. Well, that's just a guess. You can check that out with your calculator. If I replace x by 6.7, and I'm sorry, if I replace x by 2.5, do I really get 6.7? Okay. Well, actually, I don't. It's like 5.636 or something like that. You can check that out in your calculator. Well, this is a crude graph, but understanding these two things on the graph can be really important for the course.